Hello, welcome to this OCR Further Maths Statistics video, the fourth in the series, and looking at Yates's correction for 2x2 contingency tables. Because chi-squared is a continuous distribution, whereas the observed frequencies are discrete, there are problems if the contingency table is too small. We need to do a continuity correction if there is only one degree of freedom. In other words, for a 2x2 contingency table. We have already seen and used the general formula for x squared. Here is the adapted form for use with 2x2 contingency tables. You just need to subtract 0.5 from the difference before squaring. But you need to make sure that you subtract it from the positive difference, indicated by the modulus of O minus E. Here's an example. So, we've got a two-way table showing preference for chocolate or apple, and whether people are children or adults. Here's a reminder of the steps we need to take to do a chi-squared test. The first thing is to write down the null and alternative hypotheses. Pause the video while you do that. OK, you should have written down pretty much exactly this. There isn't room for much variation here, just perhaps how you've referred to children versus adults. Then we need to calculate the number of degrees of freedom. We need to do this before doing any calculations, in case we need to use Yates's correction, which in this case we do. The next step is to create the table of expected values based on the null hypothesis, which is that they are independent. Pause the video while you fill in the expected values table. OK, for children choosing chocolate, you should have got a probability of 89 out of 122 times 47 out of 122. And multiply that by 122. So those cancel. It's 89 times 47 divided by 122, and you get 34.29. You can now work out the rest just by subtracting from the totals. And of course this makes sense given that there is only 1 degree of freedom. And you get a completed table like this. OK, now we need to work out the contributions to the test statistic, remembering to use Yates's correction because it's a 2x2 table. The formula is given in the exam, so here it is. OK, for children and chocolate, you get 38 minus 34.29. You need to make sure you've got the positive difference. Take away 0.5 and then square that result and divide by 34.29. That should give you 0.300. Pause the video while you work out the rest of the table. OK, this is what you should have got for the rest of the table. If you didn't get these answers, the most common mistake is not making sure your difference is positive before subtracting the 0.5. Remember that you should always give these to 3 decimal places and then the sum to 2 decimal places. OK, now we add those contributions up to get x squared equals 1.81. And now we need to look up the critical value. Pause the video while you try this yourself first. OK, we've got 1 degree of freedom, and working at the 5% level, we're looking to see if x squared is too big, so we want the probability that x squared is less than the critical value to be 95%. So the critical value is 3.841. Now we draw our conclusion and state it in context. OK, X squared is less than the critical value, so it's in the big shaded area. That means it's not significant, so we don't reject the null hypothesis. In context, we write, there is insufficient evidence to suggest that there is an association between dessert choice and age category. That's the end of this video on Yates correction. In the next video, we look at chi-squared tests for goodness of fit.